So in these examples that I want to do today, it's more practice with identifying free body diagrams and summing the forces and then using those forces and to find acceleration. Okay, because once you have the acceleration, like the problems we did in chapters 1 through 4, technically have everything we need to find anything about the motion, whether it's how far it's gone in a certain amount of time, or how fast it's going after it's gone a certain distance, or those types of kinematics types problems. Okay, but they all hinge on us being able to identify forces to use them with Newton's laws. So as a quick review, I like to say we're going to follow the adventures of a 2-kilogram block. We did something moderate like this on Friday, but just to warm us up. 2-kilogram block on a flat surface. I'm not going to be overly concerned with sig figs. If you're plugging these answers into Mastering Physics, you should be overly concerned with sig figs because it'll bark at you. Okay, so we have a coefficient of kinetic friction of 0.2 of a surface with a block, typically like wood on wood, hovers around this coefficient, and we have a 10 Newton force pushing it to the right. Let's say its initial velocity is 0, just so we can determine the direction of the friction force. Because if you remember, the cross product between friction and velocity has to be 0, and their dot product has to be negative. And all is that to say is that the vectors have to be, anti-parallel. If you're moving in this direction, kinetic friction has to be in that direction, and drag as well. Those are two forces that are always opposite the direction of the motion. Anyway, and we'll talk about drag too if we got some time. All right, so what is acceleration here? Simple problem. Find A. Find A sub x, really. Okay. So we have everything we need. I'm gonna mute just in case folks. Of course, you can always unmute to ask a question. What's free body diagram look like? Well, we have to identify all the forces acting on the 2-kilogram block. Okay, so how do you draw a free body diagram? Start off with a coordinate system, simple XY coordinate system. Since this is a flat surface, draw our standard one, right? And then model the box as a particle. And put the particle at the origin of the coordinate system, and then write all the forces acting on the object as if it's on the particle. Again, don't do something like this where you draw a force right here for the push, and then gravity's right here, and then normal. Where do you want to put normal? Do you want to put it on the left or the right? And then somewhere there, and then friction's back here. It's too hard to work with these vectors when they're like this. I mentioned this last week as well, but you don't want to do that. You want to put them all at the same origin. And so in this case, we've got a downward gravity force as usual. Okay. In the book, we call it m times vector g, right? The mass times the free fall constant. We obviously have our push of 10 newtons. So I'll call that just P. We've got a normal force, right? In this case, this is one of the very basic cases where the normal force would be equal to the gravitational force. But when we talk about mass, weight, and gravity, that might not always be the case. And then finally, we have a small backwards friction force, which we label F sub K. Okay, N, normal force is a lowercase n. And so we should have a net force pointing to the right. F net. F net. That's a good example of the free body diagram. And so what do we, how do we use the free body diagram now? Well, to use a free body diagram, we want to sum the forces in each direction, which means everything that is in the x direction, we're going to write as a plus or minus. Sum the forces, so this is going to be, just using symbols, it's going to do plus P minus kinetic friction equals F net. but it also equals, I mean, F net equals plus equals MA, and so it's be plus M plus MA. A little very subtle remark, if you write MA sub X, then this could be greater than 0 or less than 0. But when you drop the subscript, now the A is an actual magnitude, and so you need the plus or the minus out in front. Like for instance, if it was if it was like once we let go of the push, then the force and the free body diagram is just like M, mg, and then backwards F sub k. So the free body diagram would then, or the x direction would be minus F sub k equals minus MA. That's another point. What about in the y direction? We've got N or plus N really minus mg equals 0. This looks good. So now we just look at the numbers that we've got and try and piece together what we're trying to find. We're trying to find A. Okay, so we would technically look at this first X equation and say, okay, it's 10 newtons minus the friction force equals plus 2 kilograms times A. So evidently we need the friction force. How do we find the friction force? Once again, the friction force comes directly from the normal force. Friction force, we have F sub k. The definition of the friction force equals magnitudes of them. F sub k equals the coefficient times the normal force. So in this case, it'll be 0.20 times n. Well, what's n? You just have to go back again and remind yourself, well, how do we find n? Well, in this case, n does equal mg. There's cases where it won't always equal mg. But, you know, like I said, in this case, it does equal, oops, did I write A? I meant to write N. Oh, okay, no, this is fine. Yeah, I did write N, okay. So that means N is 2 times 9.8, which is 19.6. So the friction force is 3.92 newtons. And then plugging that into the friction force, we're going to get, we're going to get 10 newtons minus 3.94 newtons equals 2 kg times A. And so now there's an algebra problem. Well, 3.92 is pretty close to 4. So 10 newtons minus 3.92 is going to be pretty close to 6. You get 6.08 newtons equals 2 kilograms times A. And then our final result is that acceleration equals 3.04 meters per second squared. So that's how some. Yeah, question. Go ahead. Sure.
Okay, so where did you find the 3.97?
Well, 3.92. Sometimes my 2s and 7s get confusing. I calculated so the normal force on the lower left-hand side here. The normal force was mg, which is 2 kilograms times 9.8. And that is certainly, I mean, it's part of my job description that I have to memorize these multiples. So this is 19.6 newtons. And then the friction coefficient, or so the friction force is then 0.2 times 19.6.
Okay, and then you said that in this case, n is equal to mg, and then in some cases it won't be. How will we know that?
That's a good question. It'll depend on the context. I give a very kind of general checklist, but kind of basically, okay, so the way when you know that it's not equal, first of all, F net, let me see if I write this correctly. F net in the y direction in this problem is 0. And the normal force and gravity are the only ones in the y direction. And so both of those kind of force n to equal mg. But if you look at like the next example, what if you push down on the block at an angle? So you take the same 2 kg block, but push down on it. Well, what is a free body diagram going to look like now? And it's a good lead into this. This question is a good lead into this actual example. Well, now if you draw the forces, same thing, same numbers and same coefficients and stuff, but now you still have mg down, and it's still the same 19.6. Okay, but now we got to push downward. Let's say if it's the same 10 newtons at some angle. Let's say it's I'm doing the calculations in my head real quick. Let's say it's, will 30 degrees work? Let's see, 10 cosine 30 is 5, so that'd be 24.6, 0.2 times, yeah, it'll work, okay, 30 degrees. Yeah, if it's a 30-degree angle, then the normal force has to be larger because, well, if F net is still 0 in the y direction, now we still have a backwards friction force. But if F net in the y direction is still 0, just go below. If F net in the y direction is still 0, what does this add to? Well, we have a normal force plus n minus mg, but also minus the push times sine of 30. Equals 0. So here the normal force is actually bigger than mg. Does that make sense?
Yes, it does. Thank you.
Perfect. Good. Good. I'm glad you mentioned this because this is a really, I mean, this example itself was also going to be a lead into kind of a broader conversation about weight, what we call mass, weight, and gravity in section 6.3. But so yeah, the normal force would be bigger, which in turn will make the friction force bigger, right? So the normal force here, you heard me doing these things in my head real quick. We have mg plus p sine of 30. Sine of 30 is a half. Physics teachers always choose sine 30 because it's a half, because it's easiest. 19.6 newtons plus 10 newtons times sine of 30 is 19.6 plus 10 times half is 5. So add 5 to this, we get 24.6 newtons. What does that make the friction force? The friction force is now, it's still 0.2. The coefficient doesn't change, times 24.6. 4.92 newtons. That looks right. Yeah, 4.92 newtons. So there's actually two things going on in this example. So if we're comparing the acceleration in this example to the previous one, not only do we have to see by pushing down, not only does this calculation show we have a larger friction force, but the effective push, which causes the acceleration, right? And looking at the forces in the x direction up here, that's p sine of, or sorry, cosine of 30 minus that bigger friction force equals mass times acceleration. So there's two things that add together, literally add together to reduce the acceleration. We've got a smaller effective push competing against now a larger friction force. And if you work at all these numbers, what do you get? 10 cosine 30 is about 0.86. So I'm just going to call this roughly 8.6 newtons minus 4.92 newtons equals 2 kilograms times A. Okay, I can do this in my head. So 8.6 minus 5 is 3.6. So adding 0.08 to that is going to give us a 3.68 newtons. That's our net force, evidently. That's going to equal 2 kg times A. Dividing by 2, we're going to get 1.34. So our acceleration now is 1.34 meters per second squared. I'm going to write below, compare to, I never know if I write the right CF, some Latin, humanities, and we'll know what that means. Compare with the acceleration from the previous problem of 3.04 meters per second squared. So evidently just pushing downward at that angle reduces the acceleration by more than half. And right, it reduces it by more than half because you have a larger, so the downward effect of the push increases the normal force. That increases the friction force. But the downward push also lowers the effective force to increase the horizontal motion. So you have a smaller force competing with a now larger friction force. And so you're left with, a smaller acceleration. Okay. On the other end, you could turn the problem around. I really enjoy doing all these problems. I would do all of them if someone paid me to do this like 24/7. I would just be like a robot that does physics problems on video. But we have enough to cover, so we have to move on. But consider what would happen if instead of a push down, if it was instead a push up, right? How would the acceleration change? I'm not going to go through that in detail. That'd be something worth considering. Is that if instead you push it up, like instead of like if you're dragging your, moving or whatever, say you're moving and you're dragging a box upward, like that, right? The same 10 Newton force, maybe it's a 10 Newton pull that's directed upwards at the 30-degree angle. Okay, how's the acceleration going to change now? Well, I'll guarantee it's going to be greater than 3.04 because now you've got now the upward part of the push is going to work against gravity, and so you're going to have a lower normal force. Right now, normal force is less than mg, and that in turn will give you a lower friction force. So when you pull up, you're going to have a larger effective push competing against an even smaller friction, so for an even larger acceleration. So those are just a few simple examples when the normal force is not equal to gravity. You even have one in your homework where, I'm happy to explain this one if folks have questions about this, say tomorrow, but I think there's an example where a box is actually sliding down, it's moving downward on a wall, and you have to push up. Well, in this example, if it's moving, well, in this example, normal force points outward and gravity just points down. They don't even point in the same, they don't even have on the same axis. Okay, what are some other examples where normal force would not be in the same size as gravity? Well, it happened to me about 15 minutes ago. 9:02, maybe about half an hour ago, in an elevator. Okay, elevator is a perfect example of where normal force is a lot different. So if we consider, say, like this would be a little few minutes that we spend on weight, okay, because what is mass? We've talked about what mass is. And this isn't meant to be like a lecture. This is meant to be like a problem, a physics sort of problem-oriented discussion so that we can really understand what we mean by weight. Okay, so mass, right, is this idea that it's a property of an object. So, the 2 kg block, right? Oh, with the 10 Newton force will accelerate at 5 meters per second squared in whatever direction. If I double the force, I double the acceleration. If I triple the force, I triple the acceleration. If I have the force, I have the acceleration. If I rotate the force, I change the direction of the acceleration, it always remains the same. That proportion is always true, and these two vectors are always related to each other. That's what inertial mass means. Okay, so if I were to ask you, how do you measure the mass of an object in space, you would say, apply a force and see how it accelerates, right? Because when we say like in space, all of us probably correctly understand that gravity is sort of quote unquote everywhere. But when we say in space, we kind of deep space, like we're meaning like far enough away from any significant measurable gravitational force. Anyway, so that's mass. What is gravity though? That does beg the question, well, what actually is gravity? Well, how much time do you want me to explain? I mean, gravity is, in our simplest starting definition, right? It's an attractive force between any objects of mass. Why do massive objects attract one another? I don't know. I mean, yeah, so we could go on and on about why that is, but we know that it's true. And this massive attraction gives rise to planets orbiting stars and stars orbiting centers of galaxies and galaxies doing something around each other, but also responsible for your pencil falling down and hitting the floor, the basketball being shot into the air, landing in the net, eventually and falling back to the ground, all these examples of gravity, okay? It's a force, but we're going to define weight in terms of some problems. So let's consider, typical person. Let's say we have the mass of a person that's 60 kilograms. Okay, and I'll also work in pounds. Let's say the mass of the person is 60 kilograms, right? On their floor, bathroom scale at home. Okay, what's the scale read? Okay, we're going to say the weight of an object is a measurement that you make that is usually some force directed kind of against the gravitational force. So the reading is the weight. So what's the FBD in this case? Well, you got obviously mg down, normal force up. And so in this very simple example, again, normal force does equal the gravitational force. So it'd be N equals 60 times 9.8 newtons. That is 58.8, so 588 newtons. You can divide that by 4.5, or more cleverly multiply 60 by 2.2. It's 132 pounds. So that reading would be 132 pounds. I weighed 132 pounds once. Moving on. So what about now if you step in an elevator? So that's the classic example now of where your weight changes when you're in a different, what we call frame of reference. So if I take this 60 kilogram person and put him in an elevator that's now moving upwards, well, it doesn't matter in direction it's moving. It matters if it's direction of accelerating. Okay, so person, my stick figure drawing person will get less and less, it'll get more sloppy as we go. Okay, so now if the person is accelerating upward, which means one of two things. They could be increasing speed moving upwards, or they could be decreasing speed downwards. So that is, you could be descending to the ground floor and stopping, or you could be ascending to the top floor and increasing speed. So if the acceleration here is, say, something like dramatic, like 5 meters per second squared. Most elevators don't accelerate at this rapid of a rate. then what's the reading here? Well, once again, it's what the normal force is. And so the free body diagram now, if you know you're accelerating, if you have an upward acceleration, let me move it over a little bit more. If you have an upward acceleration, that's going to activate Newton's second law. And so you get F net upward. Well, now does gravity change? No. And yes, you gotta love that answer. It changes immeasurably small amount. From like the first to the third floor of a building, gravity will change by probably like 0.00000001 newtons. Okay, if someone's watching this on YouTube, you can check and leave in the comments whether or not it was correct or not. But the normal force has to be bigger than gravity because we're accelerating upward. And so we've got N, minus mg equals plus ma because we're accelerating in the direction of m. And so adding those together, 60 times 5 is 300, right? So we can write all this out. You get N minus 588 newtons equals plus 60 kilograms times 5 meters per second squared. So that's 300. So you get a normal force of 888 newtons. Converting that to pounds, we get actually about 200 pounds. I didn't plan on that, but it ended up being very nearly 200 pounds, 199 point something. Okay. So quickly gain 70 pounds just by stepping in an elevator. And then of course, if the person's accelerating downward, then the weight decreases and you'll be like 50 pounds. Oh, no, 50 pounds. You'd be like, actually it'd be close to 60 some pounds, interestingly enough. Okay, so the elevator is a classic example where a normal force is not equal to gravity. And it's not equal to gravity when the object is accelerating. Other examples. The elevator, problem is interesting though. Let me take it a step further. What would be the weight? Okay, so what would be the weight of the person if we were accelerating downward at 9.8 meters per second squared? Okay, well, at that point, the F net would equal gravity. And so our normal force would be 0. So we would be momentarily weightless. Interestingly enough, let me ask you this. What if the elevator is, let's make it really horrifying, and let's ask if the elevator is accelerating downward at 19.6 meters per second squared. What would be our weight then? Any suggestions?
Would our weight be negative?
Yeah, I like where you're going with it. What would the free body diagram look like?
Wouldn't our weight be 0?
Well, what's the normal force? I guess that's the question, because when we're asking of weight, we're asking what is the magnitude of the normal force? Where's the normal force here? Okay, draw FBD. mg points down. But I've always noticed that this is a helpful example for folks. It's one that I just came up with one time. What's F net here? Maybe that'd be helpful. So 60, you know, the mass of, we're in the elevator, mass of the person, 60 kilograms, right? Just using Newton's third law itself, or sorry, the second law itself, F net would be down, and what would be the magnitude of it? It'd be 60 times 19.6. You don't have to do that in your head. It's 1176. Right? 580, if you have 588 times, yeah, it is 1176. What's gravity? It's oops. Well, gravity has a magnitude of 588 newtons. So what does that leave our normal force? It's the right numbers, right? What magnitude does the normal force have to be? And here's the critical part, in what direction?
588 newtons heading downward.
That's right. So the normal force would point downward. So if we're accelerating downward at a rate of 19.6 meters per second squared, we weigh the same 132 pounds. But down is up is down, and there we go. Right? Because everything would just kind of, if we were accelerating downward, everything would just plunge on the ceiling, and you know, everything would be attracted to the ceiling, I guess. And would it really be attracted to the ceiling? Actually, I caught myself just now. This is like a really, really important question that no one really had a good explanation to until Einstein came around and said, well, you can't really tell. This is how mysterious gravity is, that you can't really tell if you are accelerating or if gravity is exerting a force. The so-called principle of equivalence, because you know, there's something called the gravitational mass of the object. You can measure the gravitational mass of the object by considering its acceleration due to free fall at a specific point in space, right? Because we use this equation F, right? This equation F, this is true in general, m times g, but this g itself can change. Sometimes I call it local gravity because it can change from location to location, really is a function of position. And so the mass, the gravitational mass, is technically defined as the magnitude of the gravity force divided by the magnitude of the free fall acceleration at that point. But Einstein showed that that is the same. You might think it's like one special case because, like, let's say you took that 5 kilogram block or that 2 kilogram block and put it on a spring, right? And the spring kind of wobbled back and forth, and you measured what we call the spring mass. Or maybe you pulled on it with a rope, right? And you get with a certain tension, and you get a certain acceleration, and then you call that the rope mass. You call this the spring mass. You call this the gravity mass. So it makes sense that this is a special case of the inertial mass, but what's special about what Einstein said is that this gravity mass itself, this gravitational mass is actually the same thing as inertial mass. And so if you're in here's another example that's kind of interesting, is that, like, you're in a classroom, right? Someone shines a laser. Laser travels in a straight line to the end. But if you're in a classroom that is accelerating upward, what are we going to observe about light? If it's accelerating upward, we're going to observe that light appears to travel in a parabolic trajectory when you fire the laser. But, you know, light doesn't have any mass. And so we have to kind of redefine what we mean by mass and what we mean by gravity. And that acceleration in some sense bends the so-called space-time of an object. that means anything to anybody. Okay, never mind. So that's a brief overview of mass, weight, and gravity. It's more interesting than than you think, because what we mean by weight is often different in different examples. But the classic example is that of the of the elevator, and so that really gets us through like the third section of chapter 6. It looks like it's about time to go, so we're not going to keep moving with a discussion. In the next discussion, we will do some examples with drag. I'll develop some examples of drag a little bit, and just more problem solving. I mean, you want to do as many problems as you can to understand all these intricacies of drawing free body diagrams and summing the forces. And then to be completely honest, in chapter 7 is really when all this stuff really gets put to the test. And we have several examples that are very difficult, and we'll do as many examples as we can.